Hello everyone, my name is Robert and this is the video lab report for Lab 3. For this experiment we had two parts, both of which we used a computational model for in part 1 to determine the unknown mass of a black hole from an orbiting star using FNet and its velocity. And then for part 2 we had a starship and a moon and we wanted to create a stable orbit around both the planet and the moon system. For this, we use a computation model, mainly using the principles of universal gravitation and the momentum principle. And for the results, part 1, we found the mass of the simulated black hole to be 1.50, 10 to the 34th kilograms. And for part 2, I found this simulated orbit, which was stable around both the moon and the planet. So the fundamental principles for this lab revolved around, for at least for part 1, the curving motion separation of Fnet being equal to delta P, change in momentum over change in time, and we're breaking that down into the parallel components of if it's speeding up or slowing down, and the perpendicular components of whether it's changing directions as given in the equations below. For universal gravitation, we used G(mm) over the magnitude of the distance between them times r hat, and the momentum principle, force is equal to delta P over delta T, and deriving the velocity update and position update formula. So jumping into the computational model for part 1, we see that our system was the star, the surrounding was the black holes. Given the initial mass of the star and amount of time, we were first able to calculate Fnet using the velocities given to find P initial and P final. Since Fnet is change in momentum over change in time, that will give us the orange arrow as the general direction and magnitude of Fnet. Then we broke this down into Fnet parallel and perpendicular components. For the parallel component to see if it's speeding up or speeding down, from the equation that the magnitude of PF minus the magnitude of PI over delta T times P hat will give us the parallel component. Fnet perpendicular, you could subtract Fnet minus Fnet parallel, but from the formal definition, the magnitude of the P vector from P final and then the change from P final to P initial unit vectors over the change in time will also give you the Fnet perpendicular, which we use to find both the blue and purple arrows, blue being the perpendicular force in the n hat direction, and then the purple arrow in the p hat direction. Mass of black hole was found from Fnet equaling universal gravitation. Undo the equation to solve for the magnitude of the black hole, which we found to be 1.50 times 10 to the 34th kilograms. Jumping into part 2, this is where we wanted to find a stable orbit for our ship around both a moon and planet. So we were given the mass of the planet, moon, and ship, as well as the orbital speed of the moon, and these two lines at the bottom were the experimental velocities of the ship. So to find a stable path for our ship, we first wanted to calculate the path of the moon's orbit itself. So we used universal gravitation to determine the amount of force on the moon by the planet as well as the ship. But since the ship is much smaller than the planet, the ship's effect on the moon is substantially zero. We first found the distance between planet to moon using the r vector, so moon minus planet. Then we calculated using universal gravitation the planet on moon, as well as the ship on moon, and adding those together will give us the Fnet on the moon itself, so determining the moon's path. To calculate the force of gravitation on the ship, since its mass is much smaller than either the mass of the moon or the planet, both of those have a substantial effect on its motion, so we need to calculate the force of the planet on the ship as well as the force of the moon on the ship. So once again, finding the r vector using our system minus source, the ship minus planet, as well as the ship minus moon, universal gravitation, g times planet mass times ship mass divided by the magnitude of the r vector times r hat. Adding those together will give us Fnet on the ship itself is from both the planet as well as the moon. Finally, we use the momentum principle for both velocity update and position update to get the moon's trajectory path, and then calculating from our experimental values to get the ship's velocity and then its ultimate position and if the orbit is stable or not. To answer the what if questions, net force is equal to the rate of change of momentum, since F net is dp over dt. And for the second one, orbiting bodies that are pretty close in mass except for the black hole would be very chaotic, but since the black hole has the overwhelming mass, it would probably dominate if not swallow the rest of them.